It looks like we're live. People can't see you because I haven't moved it around.
Okay.
But it looks like that worked. Hello, folks. If you're watching this after the fact, sit tight. We've had some technical difficulties. We're getting going, and so check the notes doc for time codes below to know when we actually get everything going. It looks like we're working. Thank you to DCD David for doing time codes. I saw that you're here. I really appreciate it every week. And let me just pause this. And whew. So I just recompiled OBS. Yay, we got some yays in the YouTube chat. And folks can hear you, Jim, but they cannot see you because I'm on the wrong screen. So let's see.
All right.
Oh, that's...
Hello, everybody.
Now people can see you. Let's see if I can't make this a little bigger. All right. Okay, so let me do housekeeping. I think we're as good as it's going to get. If we need to see stuff later, we can tweak things. So let's do housekeeping. All right, so hello everyone. You can see me up here, that's right. My name is Scott. I work on CircuitPython for Adafruit. This is a deep dive. Oh, if you don't know, CircuitPython is a version of Python designed for microcontrollers, which are little inexpensive computers that are really easy to get going programming generally, but also interacting with the real world. So that's what they excel at. Adafruit is an open source hardware and software company based out of New York. They pay for me to work on CircuitPython, and they pay for me to do these streams. So if you want to support me, support them by going to adafruit.com, purchasing some hardware there. If you want to chat with me and a lot of others, join the Adafruit Discord server by going to the URL adafru.it/discord. We're there all week. That's not just during the streams. That's what makes Discord so awesome. This is a deep dive. They happen every week at 2 p.m. Pacific if things start on time and up like they should. But this week we're getting going about 20 minutes late. So oops. Thank you to Jim for getting up early and then waiting for me to get everything working. Normally happens Fridays at 2 p.m. Pacific. That's 7 a.m. for the Australians in the crowd. Generally they're on Fridays. We do occasionally shift it to Thursdays. We typically go for 2 hours or more. We should be able to do that this week as well if we've got enough to talk about. Questions are welcome, although we're going to get started with Jim here since he's been patiently waiting. But we'll answer questions as they come up. And then next week should be on Friday as well. I looked at that. And last up, the cat, who you can't see, is epileptic. So just be aware that if I'm like not talking and watching something, that's because I'm making sure he's okay. And there's roofers next door, so they're making noise as well. All right, well, that's housekeeping. We're going again, which is great. So who is this on the screen, Jim? Why don't you introduce yourself a little bit first? Let's start with the basics before we get super in the weeds.
Cool. All right. Well, hi, Scott, and hi, everyone. Thanks for having me on your deep dive. I work on micropython, so CircuitPython. I'm sure everyone here is familiar with CircuitPython and micropython, and I've been involved for a few years after coming from an education teaching background with the microbit, and I fell in love with micropython on the microbit, and had a lot of fun getting kids excited about computers and electronics.
Awesome. I was wondering how you got into micropython.
Yeah, it's been a lot of fun, actually, and over time got more involved and eventually met Damien at PyCon, and now I do this. This is my job. I spend my when I'm not studying, I work on micropython.
Right.
And do everything from.
So you're paid by George Robotics, right? So if you want to support Jim and Damien, you can buy a Pi board D.
Yeah.
That's a great way. And they also do contract work. So if you're looking to put it in a product, that's a way to do it too.
And GitHub sponsorship we just added recently as well, which is really awesome.
Awesome. Yeah, so I highly encourage folks to support them as well. They've done like so much great work.
Thanks.
And continue to do great work. And CircuitPython benefits from the micropython work. So thank you, Jim, for working on that. And thanks to Damien and all of the other micropython contributors as well.
Thank you.
Yeah, so I think that is a good introduction. So you reached out. So we had a discussion with us, and I said, Damien, Jim, if you ever want to come on our deep dive and talk about something, let me know. You're welcome. So what made you email me and be like, hey, I've got this thing that could be fun to talk about?
Well, I think I'm very excited about your recent work to merge up to 1.16 to CircuitPython. It is a really good opportunity for us to bring the two forks even closer together. And the day with much of the code base is the same, and our bugs are your bugs, and and I thought it sounded interesting. I like learning and teaching, and certainly I've spent a lot of time banging my head against micropython and trying to figure out, like any code base, that's large and complicated, trying to get my head around how things work.
Right.
And we had this an issue that was reported, a compilation issue, and those are pretty serious, obviously, because they lead to incorrect execution of code. And
right.
Thought it might be the sort of thing that you'd like to dive into, and in the process, I'm happy to take this wherever people want. I'll full disclosure up front. I have actually already diagnosed and fixed this bug, because watching me struggle against this live would have been terrible. But
I mean,
if people have questions,
so we do actually have a tangential question from a couple folks. What is that black box with the blinky lights on the wall?
What is the black box with the blinky lights?
Under the bookshelf.
That one?
Yeah, that one.
That is my CPU. So when I was teaching, I used to want to teach how computers worked and demystify electronics, and you can start with AND gates and you can finish with micropython, but there's this big jump in between, like how does logic happen and all that.
Right.
And so I used to teach a little course on like 4-bit microcontrollers that you could build out of and basically 7400 series logic. And it wasn't quite enough. And then I discovered my two favorite websites on the internet. One is Megaprocessor, which is the guy that built out of TTL transistors, out of BJT transistors. An entire CPU. If you haven't seen it, microprocessor.net I think is the website.
Okay.
Microprocessor.com, and there's this great line in it, because you can imagine it's enormous, and it's like, at this point the battle between my living room and the microprocessor begins to escalate. So obviously too big, and then at the other end of the spectrum there's the Monster 6502, which is somebody built a 6502 processor out of surface mount FETs. And the cool thing that both of these projects have in common is that every single gate has an LED on it. And you can single step the processor and watch every single gate change state.
Right.
And so that's what that is. Except rather than being out of individual MOSFETs, it's small logic units. So like one logic unit is a register, so like 8 flip-flops or whatever.
Okay.
And anyway, topic for another.
I was gonna say, so 2 questions I have follow-ups.
It doesn't run micropython.
That was the first one. The second one was how long does it take to compile micropython?
So right now it's running. I leave it on all the time because it's one of those projects that like gives me a huge amount of satisfaction that It's just done. I'm really happy with it. And
Right.
it sits there in the background computing prime numbers.
Ah.
And I don't know, it's 100 and I can't really quite see from here, but it's what is that? The clock speed is artificially really low, and so it's
Right.
I think it's on 157 at the moment. And,
I see.
But yeah, you can speed it up. So now it's scrolling through the phone numbers. But anyway,
That's awesome.
But what it can do is drive dot stars. So it's got memory mapped IO and enough to bitbang spy. So that's quite fun. Anyway, so
Awesome. Nah, this is perfect time. Okay, props to Mr. Who 30 and Mark Olson who asked that question. I usually do say hi to folks who are in the chat, but we've been trying to get things going. All right, so let me get some windows arranged so that we can have on the desktop so we can follow along. So if folks have questions, feel free to ask them. I'm going to create a new scene here and actually just call it desktop with guest 2. So I need to add, oops, sorry. So I know you're seeing a black screen. Don't freak out. I will add me. And I will add my desktop. Window capture. Screen capture. Yeah, there we go. There, now we can see Jim. So this is going to be a bit of a challenge. That I only have so much screen space. Oh, you know what? We can put Jim beneath what we're looking at. But then I can do window capture on Jim. What I'm trying to do is get it so that folks can see both of us and my desktop. I think that would be ideal. Because I assume we're gonna want to talk about the code that we're looking at.
Yeah.
So let me just.
Should I be sharing my screen or?
I think I'll do it. I don't want to. I already had too much technical difficulties here. So I think you'll have to show me what you want.
Okay. Have you got a
browser?
Okay. Have you got the you've got the Unix port set up and ready to go?
No, I do not. Should I have that?
Yeah, we'll need the Unix port. Can we give it a go and see how it works? Otherwise, we can certainly give it a go.
You could try screen sharing. We could set that up if you'd like to drive. People are putting up with us.
How does that look?
I'm gonna have to change the clip. But... Oh, that might be. How's that, folks? Is that too small? You might want to make things bigger. This actually saves me. Yeah, and that we can only see. Oh yeah, that's your terminal. Okay. Let me send myself to the background. And that's just about... All right, can folks see Jim's screen? Enhance.
Or enhance?
Can't see the file list.
Don't worry about the file list. That's fine. It's just taking useful space.
All right, I think that's as good as we're gonna get. Does the drop saw run micropython?
No, but the laser cutter runs Linux. So.
All right, take us away, Jim.
Okay, cool. So this was based on a bug that was reported about a week or so ago, and this is exactly the repro that was given to us, and I guess what it's doing is it's turning a single integer into 4 bytes, and pulling out individual bits in that byte in that integer to set the 4 bytes. And so I should be able to run this on a so I've got a Pi board plugged in. 7.5. And as to be expected, the 4 bytes I get a 255,000, because the input was 0, so these 3 conditions should be 0. So no surprises there. That's good. So MicroPython has this feature that CircuitPython as well, Python.native. And what this does is it tells the compiler running on the board, other than generating bytecode for this function, generate native code for whatever the architecture is, which in this case is ARM thumb. And it's supposed to be, you just don't even have to think about it. You just turn it on, and everything is the same.
Right.
The native decorator just compiles it to native code, and no features are missing. There is a Viper emitter, which we can talk about later, but the native, and the only reason you would not native everything, and in fact, in the very early days of MicroPython, like before it was released publicly, Damien's goal, he told me, was that everything would always use the native emitter for performance. So MicroPython wouldn't have a virtual machine. It would just generate native code for everything. The problem you have is that native code uses a lot more, because MicroPython has to execute its code from RAM, so it compiles, generates the in RAM. It takes up a lot more RAM for the same functionality. So this same function would be a lot bigger in native code.
So could you? Sorry, I'm gonna pause. Could you make your terminal bigger?
Yeah, of course.
Your text bigger there. Folks are having a little trouble seeing that. That looks better.
Cool.
I can see it better than other people too. Okay, so that's interesting. So I was gonna ask you, like, what is the reason that people would use the native emitter?
Yeah, entirely performance. If you can afford the RAM for a couple of small functions, and the RAM overhead's about double, I think, from memory, and it varies a little bit depending on the function.
Okay.
And the reason for this extra overhead is that in MicroPython, like cpython in bytecode, you can express quite a lot in one opcode. So an add on the top 2 things on the stack or whatever, and whereas expressing that in native code, you have to actually emit any potential checks, any literally everything the CPU has to do to implement that one Python high-level instruction has to be generated as potentially many bytes of machine code. And you think about something really simple in Python like a plus b. You've got to figure out the type of a. You've got to figure out the type of, well, sort of. You've got to figure out which method to call on them and things like that. And the details here are a bit complicated, and there's a lot of optimizations. But when your competition is a 1 byte opcode, it's pretty tough. So
right.
And so a long time ago, MicroPython switched to generating bytecode by default.
Okay.
And you move the cost into Flash, because all of the code for the VM is in Flash, which you generally have more of.
Right.
And you put a lot less in RAM.
Right.
And this is the benefit of freezing your Python code, is because when you freeze it, the code goes in Flash as well. So if you're freezing, it's worth considering using native because it'll get a big performance boost. Yeah.
So I just wanted to point out for those folks who are like not classically trained computer science folks, is like this is a classic trade-off. This is a classic trade-off of space versus execution speed. And so that's not surprising to me at all.
Yeah. There's a surprisingly large amount of things like that in MicroPython, and I guess that's true. I guess that's true in any software project, but it's always finding the right point in trade-off space, and Scott and I have talked about this a lot before. But there's lots of features that we would love to provide more knobs to the user to decide what their code does, but we have to maintain Python compatibility.
Right.
Things like the native decorator obviously are about as close as you can get to keeping Python syntax while still giving a few hints to the compiler. So.
One thing that I did do pretty early on when I was working in MicroPython is I really pushed Damien to require a MicroPython import. For stuff like this, which I think you can do. I think you could say import MicroPython and then it will work. But that was something that I was a little nitpicky on. And the reason that I was nitpicky on that for folks is that if you took this code without the import for MicroPython and tried to run it in cpython, you would get an error because MicroPython was not defined.
Exactly. And you could write micropython.py that had def native.
Whatever the arguments are,
returns f, whatever. And then if you had that in the old path or whatever, then this would just run on CPython as well. Yeah,
right.
Exactly.
Right. Yeah, and where we see that most is like if folks have ever seen the const thing in CircuitPython or MicroPython code, const is the same idea, is that like MicroPython knows to just use it on its own when it sees it, but we kind of enforce in CircuitPython libraries that you need to say like from MicroPython import const, and that allows us to have a const thing in Blinka that just passes the value through, just like Jim did for native as well.
And so for people who are interested, this example code wouldn't get any benefit from this, but if I had a program that I had some variables I'm using lots of places, I can do these two different versions of the const keyword with and without the leading underscore. And what that means is that anywhere I use these variables A and B, it's not really a global variable. I'm not having to do a lookup into the global stick. It literally is as if I typed 20, like I have with these other literals. And then the B has the underscore version has this extra thing where it no longer even becomes part of, as well as avoiding being a global lookup when I use it here, it also doesn't even add it to global, so I can't even use it from outside the module. So it literally has zero RAM cost at all. So
right, and that's what we found is like we tend to only use const for the things that are because I think people don't always realize that there's a RAM cost to variable names. Like the variable names are stored in RAM for all this stuff.
Only global variables, and actually that's something we're going to talk about because local variables, the variable names don't exist.
Okay.
Only the globals.
Right. Okay. So what the native decorator is, so for those new to Python, the @ symbol before a function is called a decorator, and functionally the way it works is that thing gets called with the function passed to it, right? If you were thinking of classic CPython. Now, MicroPython is playing tricks here when it sees that, but that's generally like why it's valid Python. So the native emitter emits thumb code. It's larger RAM. It takes more RAM than the VM bytecode, but it runs faster. Do we do much optimization with that thumb code? Because I had somebody say like, oh, that's like GCC or something. I was like, well, it's not quite a compiler.
It's way faster because because obviously the VM has these huge costs in like it's the VM is just a while loop with a bunch of if statements and all these branches and stuff like that.
Right.
So it is really fast because it linearizes the code, I guess. But no, there's very little optimizations. But I guess that's a good time to talk about. So we also have this thing called Viper.
Well, wait, we have a question here. Let's keep up with.
Yeah, sure.
So the question is, what's thumb code?
Oh, yeah, sure. I'm probably going to mess this up, but so we're talking about generating native code for the target architecture, and
right.
on our PCs on x86, that would be x86 machine code,
right.
and or more recently 64. On ARM, historically ARM has two sort of similar instruction sets, ARM and Thumb, and Thumb is what we run on Cortex series microcontrollers.
Mm-hmm.
I will not even attempt to go into the distinction on those, but when I say Thumb, then Thumb is the name for native code on ARM.
Yeah, so I want to tie in two things here. So Thumb is an instruction set architecture, which is usually shortened to ISA, and the way that I think about it for folks who don't quite understand what this is it's really the API between software and the CPU. So it's what are the bits that the CPU load to decide how to execute. That's kind of what I think of as the ISA. And then the other thing I wanted to tie to is folks have probably heard of RISC-V. And people say, do you support RISC-V? Do you support RISC-V? And RISC-V itself at its core is just the definition of what the ISA is. It has no bearing on the actual chip, the actual CPU, like a Cortex M0, for example, right? The ISA is this API that anybody can implement, whether it's open source or not open source. And then the compilers then convert human readable C code or whatever code down to that machine level instruction sets. So I just wanted to take that opportunity to talk, because I hear about RISC-V stuff all the time, and we support RISC-V, but RISC-V is not the thing that's hard for us to support. It's all of the peripherals that end up in a chip that has a RISC-V CPU.
It's a great point. Yeah,
so I thought I'd just point that out since we're talking about Thumb. And one characteristic about Thumb and RISC-V has an extension for this too is code size. So when you take some sample C code, how big is the data that the actual instructions are. And Thumb 2 is the second revision of Thumb, and it has a lot of 16-bit instructions, which means that it is much smaller generally. And you can find comparisons about the compressed instruction set for RISC-V and see how different code size matters between those two things.
Yeah, and it's funny because R in ARM originally was RISC as well, and RISC here is the reduced instruction set computer or whatever it is, and but these days when you look at ARM and look at Thumb and things, it's not really very reduced anymore.
Right.
I mean, we talked about the CPU on the wall earlier. That has, I think, I don't know, it's 10 instructions or something like that. But nowadays on ARM you can do things like add this with a dereference and an offset, and because ARM's got this barrel shifter that can do all these fancy calculations inside an instruction. And yeah, it all gets pretty complicated.
Right.
But I will link after this. There's actually, if anyone's interested in intro to Thumb, Raymond Chen on the Old New Thing blog has just recently done a 25-part series on Thumb, and it's amazing as everything he writes is.
I should read to that. And I also want to, so RISC is reduced instruction set, and that the corollary is C complex. Is it complex or?
Yeah.
So x86 is generally known as a CISC, not reduced. And the idea, as Jim started talking about, as complex or instruction sets have these very long instructions that can do a lot all at once potentially. But I think the world's going towards reduced instruction set stuff, and if you read about the design of the M1 the ARM chip and the M1, one thing that they really do a lot is like if you have fixed length instructions, it means that you can look ahead really far into like the things that you're going to potentially do in the future. And the advantage of that is like if you get into computer design, which we're in these weeds, which is great. That's what deep dives are for. Is that the challenge with any CPU is generally that your memory is a lot slower. So it's really beneficial for chips like the M1 where they can look, I think it's like 128 instructions ahead or something, and they can initiate all of the RAM lookups that may need to happen so that just in case they need that data, it's closer and it's already on its way. Versus the like x86 model where they can't necessarily look that far into the future because they don't exactly know where their instructions are.
Yeah, bigger and bigger hacks to try and figure out what the dependencies are and stuff like that. Yeah, so when people talk about a CPU having deep pipelining, that's what they're talking about. It's that the pipeline is really long because they can be
right.
Well, sort of. There's a lot of concepts here.
And yeah, but we're in the weeds because another related thing.
I found my home. This is amazing.
No, it's great. I mean, that's what people come for. The other thing to, if folks have heard about the security issues in CPU designs, it has to do with this speculative stuff that the CPU is doing. So the idea that you can go into a branch of code and it will say like, oh, I might need this memory in the future, therefore I'm going to go fetch it. But then like you didn't actually need it because you weren't allowed to fetch it. But then if you can fetch it in another way, you can see that like it was cached. So there's a whole like, meltdown. There's all these sorts of CPU vulnerabilities that are about like things that CPUs do ahead of time just in case they might need to do it, and then making sure that like that doesn't impact like code going forwards is a huge security thing that a lot of CPUs have really been having to deal with, which is interesting, but not something that we need to deal with in MicroPython land.
So there are two things that I think that are worth bringing up there though, is that you have hit on one of my secret hidden agendas for this deep dive, which is that it would be really cool one day to get a native emitter for RISC-V for MicroPython. Mm-hmm. And so in making awareness of how the native emitter works, I hope to somebody might get excited and we'll have a little look at how you write a native emitter for MicroPython. And so RISC-V support would be really cool. And
nice.
There is one RISC-V chip that we're going to see a little bit. MicroPython effectively is already on the way to supporting, which is and CircuitPython 2 I understand is the ESP32S. Is it the C3? I think
C3,
it's the which is at its core RISC-V rather than the extensor of the previous generations. So,
right.
And like you say, it's about supporting the peripherals, and so the IDF takes care of that for us. So.
Right. Yeah, I mean, the main thing for us is that it doesn't have native USB. So we have to we would have to get BLE support through the IDF, and then we would be able to do those as BLE only boards, which is something that we do want to do, but we're in the weeds of BLE right now, as folks who've watched the stream know.
But I sympathize with you, Scott. That's what I'm doing on the other side as well. So.
Yeah. Well, some of the weeds that we're in actually now though is like I talked to you about this file transfer protocol for BLE, and we actually have the challenge now is it's not so much the device side. Like there's bugs on the device, but the main challenge for us right now that we're in is actually having apps and code that support it on the host side. So that's really like where we're trying to push right now is like. I was doing web Bluetooth stuff, and I was very pleased that like this protocol does not use L2 cap stuff because like that's not available through web Bluetooth. So I think we're on the right track with this file transfer protocol stuff over BLE, but like we just don't have the apps right now to make it worthwhile and a good experience. So that's kind of where we're pushing right now, and then like we'll cycle back to the device side once we can actually like get people testing it and finding the issues that we have.
I'm going to resist the temptation to follow that side quest and talk about L2 cap channels.
Yeah, well, I did hear from a couple of the Chrome people, so I'm looking forward to the Chrome web Bluetooth support improving.
Oh,
And
good. Okay.
hopefully actually getting them using CircuitPython to test with, which would be amazing. Because they're working on supporting secure characteristics in Chrome OS and Windows, which they don't do currently. But that I've set CircuitPython up to use. Because imagine you have a room full of people and like blah, blah, blah. So.
Hey, don't use that. You keep tempting me with Bluetooth side quests. But...
Okay, let's pop the stack. Let's pop the stack back to this.
We'll do some stack popping later as well. Cool. Okay, so the thrilling conclusion is that I add micropython.native, and I expect it to be exactly the same based on everything I said before, but unfortunately it isn't. And we see this second byte is 255, which is clearly wrong because
you passed in a 0.
I passed in a 0. 0 and 1 is 0. I should hit the else 0 case.
Right.
And that's a worry. And in this case, we're running on, so NPR is MP. This is MP Remote. It's a new tool for MicroPython.
1.15, right? It was released with
yeah.
1.15 or 1.16 is out. 1.16.
Yeah. What? Yeah. So NPR is what's your equivalent? It lets you it loads a file into RAM without touching the file system, and then executes the file out of RAM. It also lets you do this quite neat thing, which is you can go npr mount home/mpy, and now I'm on the REPL on the device. If I go and I can go import b7523, and what it's actually done is made my host PC's home/mpy directory the file system, like it's mounted into the VFS on the board.
Right.
So this is really neat for this sort of debugging, because if I just reboot the soft reset the board, I could have edited this file and so I changed that to a 1. Import b7523. Well, that's actually the right answer now. Anyway, yeah, that is.
Right.
Cool.
So this is kind of so if I had to summarize what the advantage of this is that this is kind of the CircuitPython workflow, but it's over serial only. So if you're using like an ESP32, for example, which we don't support in CircuitPython at all, like you can have this standard workflow that has file system stuff across devices, even if they don't have native USB.
Exactly. Yeah. And with very precise control about when the reboots happen and stuff like that. But and no contention on file system access, because there is only one file system. It's the host file system.
Interesting. So you're like completely losing access to the native one.
I mean, it's still there. But I haven't disabled it. But yeah. I mean, because this is an STM32 board, it has that. But
right.
But yeah, we almost never use that.
Interesting.
Okay, so it's failing on. Do we want to talk about Viper quickly?
Do whatever you like. We got tons of time.
Okay.
I mean, we started 20 minutes late. We've got at least an hour. So.
So we've also got Viper.
Okay.
Viper is also failing here. It's giving the wrong output.
Okay.
And so what Viper does is it says, first about does the native emitter do any optimization? And it doesn't. It just writes the native code that would execute the same thing that the VM would have done. What Viper does instead is say, well, I know a little bit about this code. For example, I know that packed is an integer. And so when I call, say, for example, and or add or any operations that involve integers, don't go through the normal Python implement, the dunder add or whatever. So it is an integer, emit the code as if it were that and not really a Python object. And this enables a ton of optimizations if your code is doing a bunch of number crunching. And it can be hard to get right because you have to tell the compiler exactly what all the types are. Right. And it can only go so far with its inference and whatever. It falls back to native, so like if you do regular object equal sort of things. But when it knows what the types are based on the argument annotations, it can be really, really fast. So nice. You might get yeah, another 2x performance boost from Viper.
I didn't even realize. Okay, so Viper is actually like super native. Like it's better than regular native. I didn't even realize we had any sort of logic in MicroPython for based on type hints. I didn't actually know
that's the only place the native emitter. Yeah.
Okay, but we can put type hints basically everywhere, and we just ignore them otherwise, right?
I've forgotten. Definitely in function arguments.
Okay.
And I can't remember what the state of type hints everywhere else is. I think there's possibly an outstanding PR to do that, but again, it's in that case it's in complicated one. It's extra code size for a feature that does nothing. But on the other hand, it lets you run unmodified Python code, so it is a good feature.
Which is where my interest comes from. Is like, I think the killer feature of type hints is actually just IDE help. Like, actually, it's just like making editors smarter about what things are. So if we could have like type designations in our libraries, like that would be really beneficial.
Yeah, absolutely.
So before you get going in, mCauser has a question for you.
Yeah, I just saw that. This is about the consts.
Let me read it in case sometimes we have folks that are only listening and not watching. So sure. I'll read it off. It says, if you have repeating numbers like 255s and zeros, is it a bad idea to make them consts? Are they already treated like consts internally?
Yeah. So the question is basically, if in this code on the screen, is there any benefit to me doing all ones equals const 255 and then changing these 255s? And the answer is no, because what const is doing is actually injecting the 255s into it's as if I had written, wherever I use all ones, it's as if I had written 255.
Right.
And so why this is important is if instead what I had done is I had a variable that wasn't const and done this, the generated code for this would have to look up all ones in the globals dict. And so there's a few steps here. You've got to load a qstr, so the name of this variable. You've got to look it up and then do a dictionary lookup, and then put it on the stack and stuff like that. So that can be really slow. Right. Whereas if I write 255, the generated bytecode literally has load fast 255, which all it does is like 1 or 2 byte instruction to push the value 255, not 2 byte instructions to push the value 255 directly onto the stack. And so const is just like, if you're a C programmer, const is like hash define in C. It's a substitution in the code, like a literal substitution.
Right. If you don't have the underscore in front of the name, though, you will pay a RAM price for the name itself.
Yeah, we still put it in the globals dict. So yeah, what you can do is you can write, without the underscore, you write all ones. You can use that in your code, but you could still, you could import this file and still go that file to all ones. So it kind of gives you a hybrid of both, which can be useful. Cool. So we have a native decorator on this function that does the wrong thing. So the first thing I always do at this point is
is there a way to disassemble the native output?
Exactly, and that's where this next fork we're going to take, and depending on which way this fork goes, it will greatly change the outcome of your day. So there's definitely,
it's just about weekend for me. So
fortunately, I know where this goes. So on MicroPython, sorry, I'm not as familiar with CircuitPython, but on MicroPython we have a port that runs on Linux.
Yeah.
The Unix port, and it effectively is a bit like a CPython replacement.
We still maintain the Unix port because we get all of your really good tests.
Yeah, of course, very important for running.
So that's the one that we do not get rid of.
Okay, so sorry, I should have built this before, but
you called Blaze. So for folks who don't know, Blaze is like the internal Google name for making stuff. Jim and I are both former Googlers, so
I worked there for a long time, and it was burned into my muscle memory that's how I build things.
That's hilarious.
And what else to call my alias for in parallel.
The open source version is called Bazel for those who followed along.
And a Google running or Blaze is like make-j 6000, so it's like it's pretty awesome. Okay, so now I have a MicroPython binary for Unix, and now I can run that with that same E7, whatever it is, and then we hope, yes, same failure.
Yay!
So now I don't have to debug it on the board, and if the failure had only been on the board, then I'd know there's a problem specific to the ARM emitter. Whereas this tells me this problem is common to all them. Well, at least x86 or x64 and ARM. But more importantly, I can just debug GDB natively rather than wiring up an ST-Link or whatever.
So Doctor is asking, the -j is how many threads you're using to build, right? Yeah, it's like the number of concurrent things that make has to do that it will do at the same time.
Yeah.
And generally you want it per thread.
Yeah, these days when you have nice modern fancy CPUs, it will literally make your build 16 times faster.
Yeah.
If anyone knows if there's an environment variable that you can set that just makes that the default, then I would love to know that.
I know Ninja does it by default.
Yeah.
Ninja figures it out.
And if you use -j on its own, I think it makes a sensible guess. Okay. So just as a useful thing, let's turn off let's just confirm that it does the right thing without native, which would be good to know, which it does. So one thing the Unix port does that's really quite neat is you can run with the verbose flag, and I think it's -vvv, and it tells you what it you asked about, disassembly and stuff like that, and it tells you what's going on. So I'll run through this quickly because understanding this is pretty important first to understanding how the native emitter is going to work. And so we've run the compilation on this file, and there are kind of two functions here really, which is one is there's the module itself, because at the end of the day, running a Python file is running all the lines in that file, and then each function itself is then obviously another function. And so what we're seeing here is a code block for the module, and this is the generated bytecode. So this is the bytecode that tells it how to import MicroPython and run print unpack 0. And there's a lot of there's a little bit of a preamble here. So that might seem like a lot of bytecode, but there's a preamble here, which is like defining the module and all that sort of stuff as well. And yeah, so this is MicroPython bytecode, which is different to CPython's bytecode, what it would store in a PYC file, but has a few things that are similar, but it's just a little bit more optimized for space rather than other things. And MicroPython's virtual machine is stack based, and actually we don't see a lot of. Oh yeah, we do see some stack stuff here. So we do an import of the name MicroPython, and then we assign that to the global variable called MicroPython. So this store name is a set of a global variable. We're going to make a function that is a pointer that we're going to reference later. We are going to push the name. We're going to store the name unpack. So unpack, these two lines here are make a function, push the result on the stack, and then store the current top of the stack into a global variable named unpack. And if we looked at the disassembly, if the actual bytes here, what this would be the opcode for store name followed by the qstr ID, so the intern string ID of the string unpack, which would be built into our. Let's not go down those weeds, but the point I want to make here is that the bytecode doesn't store the literal bytes unpack. It actually puts that into a table of unique strings, and then we just reference each string by its ID, so it'll be a 2-byte ID instead. Then we load from globals the name print, so we look up print in globals. So this is kind of equivalent to a dictionary lookup, but specifically in globals, because we're going to do a print statement. And then we load the name unpack, and then we load a const small int 0 So that's the 0. So that's push the literal value 0 onto the stack. And
Right.
this kind of ties into what we talked about before. Because it was a literal 0, the value is encoded into the opcode. And then we call the function the top of the stack with this many arguments. So we expect the top of the stack to have a function and one argument,
Right.
which we then execute. And then we call the function that's now on the top of the stack, which was print that we loaded earlier. It has one argument, which was the result of this previous one. We don't care about the result of print because we're not doing anything with it. Print's returning none in this case, but we do nothing. And then the module itself is a function. It returns none. So push none, turn the top of the stack.
So one question is, how wide is the stack? Does that make?
Yeah, we are gonna talk about that later.
Okay.
Yeah,
there are two ways of the stack being implemented, right? There's like intermingled in the C stack, and what we've turned on, which is we have the pi stack enabled now.
Okay. Yeah. Okay. Yeah, we're gonna talk about that too.
Perfect.
But yeah, there's actually three stacks that we're gonna have to think about to debug this. So, and then this is our actual function, the unpacked function, and it's the bytes function from built-ins from global. Load, and now we see this load fast, and load fast is a load of a local variable. So I said we throw away the names of all the locals, and the locals just become we figure out how many local variables we need, and there are just n of them in the function, and so this is the 0th one. And it's had to generate a few temporary ones, but we see we load a 1 and we AND it. So load fast 0 in this case will be the packed argument to this function.
Okay.
And so your locals are effectively your function arguments and any local variables you create after that point. So we've pushed the 0th argument onto the stack. We've pushed 1 onto the stack, and then we call the AND function.
Yep.
And so the binary op instruction says execute a binary op, and I guess this is a good time to look at it as any runtime.c mp binary op. And so the binary op code is telling the VM call mp binary op with the left-hand side and the right-hand side. And in this case, the left-hand side will be the top two values in the stack, which will be a 0 local variable, and the 0th local variable and 1 the literal.
Right.
And then the AND is encoded as an ID. So AND might be the ID 3 for binary op 3 or whatever. I don't know what it is.
Is that what the 24 is?
It could be.
24 is the MP binary op and or whatever, right?
It quite probable. I could check that.
It's probably on the int.
Yeah, it almost certainly is. But
so for those, MP binary opt is usually also implemented on a per object basis. So you can have different things happen depending on what your left hand side is. Which might actually be where you're going as in object int. Would be my guess.
Yeah, exactly. And so mp binary op then has to do all the logic of Python, which is what is the op, what are the types, and so there's a special case here, which is that if both of these types are integers, then we don't need to do anything special for integers. We can literally call, you can actually see the bitwise operators here doing their thing.
Right.
But if they're not that, then you'll see at the bottom, we need to then go and find out what the types are. So the left-hand side has a type. That type might define its own binary op, and it might do so because it's a built-in type, or it might do so because type literally defines under and, for example. And this would, if the type were instance type, then instant type's binary op knows to look at the Python code and figure out if it has an AND method.
Right.
And And this ties into the native emitter because the native emitter doesn't know anything about any of this. All it does is knows how to emit machine code that can call this same binary op function.
Right.
That's where Viper comes in, is that Viper says, but if the types were integers, then I will emit machine code for integers.
I see.
So this is a pretty nasty little function to look at the disassembly for because, it's got a couple of nested expressions and a bit repeated.
Right.
But probably the most useful thing that we can do here is to reduce the error down to the simplest possible thing. So, like, for example, does it happen if we get rid of all these extra bits?
Right. So a question from Doctor is, what is an emitter? And
yeah, cool. So an emitter, the stages go, you take the input source and you lex it to turn it into a series of tokens. So, this becomes print, open parent, so identifier, open parent, integer. That goes into the parser that builds a structure out of that. So, first argument to print is this expression, and this expression is, and then once you've got the parse tree, the emitter takes the parse tree.
And that's the stage that will tell you whether you have a syntax error.
Exactly. So Lexa will be like, I can't even figure out, if the Lexa would have an error, for example, if you didn't terminate a string or whatever.
Right.
Or if you had like completely invalid character. Yeah, I'm trying to think of a good example of that. But I'm pretty sure, like, if I wrote like triple and like that many ampersands, the Lexa would fail because it wouldn't know what token that should be, for example.
Right.
The parser would say, no, wait. I was about to say trailing comma, but is that valid? I can't remember.
I think
that
it
would be
is.
invalid. That's an invalid
Right.
expression in Python.
Right.
And so the parser would be like, there's no right-hand side to this plus operator.
Right.
And then once you've got a parse tree, you walk the tree and you emit code for the parse tree.
Mm-hmm.
And that's where you either emit the bytecode. And so the example we've been looking at here is emitting the Python bytecode for these functions.
Right.
But we also have these two other options, which is we can emit native code or we can emit Viper code. And
so the native and Viper stuff does not kind of go through the Python bytecode first. It goes straight from the parse tree straight out.
That's right. But the relationship between the Python bytecode and the API between the parser and the emitter is fairly close. It's not quite the same, but there's a lot of similarities. And so, and we should take a look at that. So, emitbc. So this is the bytecode emitter, emitbc.c. And so, for example, emitbc binary op. So what this means is the parser has found a place where it needs a binary op to happen.
Right.
And so it will write out the bytecode for binary op multi with this particular binary op. And so actually we can look up if that 24 was, I'm guessing that, that's in place and. Do you reckon that's 9 plus 13, 21 plus 3? Yep, that's 24. So
right.
that was that from earlier.
Right.
And so then we call emit right. So the parser has called emitbc binary op. And so the problem is that this happens through some preprocessor stuff. There's no call to this because what's really happening is compile.c. So compile is the thing that takes the parse tree and calls the emitter.
Mm-hmm.
And so there, for example, is a in-place add. The emit arg is a processor macro that will ultimately call
binary output like that.
Yeah. And what it comes down to is it'll figure out what the current emitter is. But emit arg will figure out what the emitter is and call the correct method on the current emitter, which will end up here. And so there'll be an equivalent in emit native. There'll be emit native binary op.
Mm-hmm. Right.
And what this is going to do is I'll skip this if statement. I'll come back to that. Is
it's a lot longer.
is this case. This is the common case, and it's saying tell the so this is the native emitter. Tell the current architecture to pop to emit the preamble, popping register register. Come back to that, and depending on the op, we emit a call, and this will literally, in whatever the current architecture is, emit the machine code that will execute the MP binary op function that we were just looking at before, and it's going to do it with so emit call with immediate arg. So it's call to some function. I want you to call the binary op function, this particular op, which was 24 from before, and I want to I forget, it assumes, I think, I can't remember which side is the left hand side, but then this will be the right hand side. Then if it was the not operator, if it was the not version of an operator, then we invert it to call the unary op function. But importantly, we're generating native code that is just calling back into our runtime that knows how to deal with these objects.
Right.
And all of the handling of what type of object is this is still happening in the regular path that the bytecode would have gone by. And similarly in vm.c, this is the case for, so this entry is like a switch statement case, and so it's the current op is a binary op. I pop the two things off the top of the stack and I call MP binary op. So we've done an if statement to figure out the current instruction and call binary op. Whereas this case is I've written machine code to explicitly call MP binary op.
Right. So mcauser asks, is native and Viper just a method level, or can you do it on the class level too?
I have no idea. That's a really good question.
To some degree, classes do function like functions.
Yeah.
In the same way that like a top level file works like a function as well.
We can find out, but at the point where you're using native on a class, you're generally better perhaps to be.
That's not per instance. That's just like when you create it the first time, right? Like the body of a class is only called once.
Yeah, so whether or not that would apply to the methods inside, I don't know. What you're probably better off doing in that case is putting it in a file on its own and then using the cross compiler to generate an MPy. And one of the arguments of the cross compiler is native everything, regardless of what decorators they have on them. And so that's what you use if you want to really optimize like an entire Python file or whatever.
And Doctor was commenting on the laughing. That's just because my windows are open and there's people outside. Bruce says this is almost as low as you can go, almost, and I totally agree. And I also want to point out that like
we're not even halfway yet. We're going to start looking at disassembly soon.
Yeah, just hold your horses. I want to point out that for folks like me, I've been working on CircuitPython for like 5 years, and I've never gotten this deep in my work. So it's really important to say that like as CircuitPython, this is the huge value that we've gotten from building on MicroPython. Like a lot of this comes from Damien and Paul and other MicroPython contributors. Like somebody asked me one time, like, how would you do CircuitPython differently if MicroPython didn't exist? And I just said, like, I wouldn't have ever done CircuitPython without MicroPython. Like this stuff is the stuff that like is way over my head and kind of not my forte. So like this is why we should support the MicroPython folks like Jim and Damien, and why CircuitPython is what it is and feels like Python is because of all of this really detailed work that like I am certainly not suitable for doing, but obviously Jim and Damien are. So this is why we should support them.
Thank you for saying that. And like let's be really clear, this is all Damien. I jump into this about 1 week a year, and when there's an interesting bug that I just because my curiosity gets the better of me. But if you look at the file history, for example, in native, It's popping up on my other desktop, but anyway, it's only Damien that pretty much that works on this, and it is really cool. Like, and so he often says like, it's not clever, like it just is a compiler, like it just is a compiler, as if like that's just a thing that someone just would write. But it is. I actually really enjoy coming here because it's not that easy. I have the benefit of having prepared for this and reminded myself of how the details work, but there's a lot of things in here that like they work the way they have to work. Like you've got to implement binary op, you've got to figure out what the types are and stuff like that.
Right. It takes like so much detailed work, and that's like definitely not my forte. That's definitely Damien's forte, is like they're really detailed, like the fact that there's a whole test suite on top of this that can make sure that it works as is, or as intended, is just really like incredibly valuable. Like
any software project, it's a combination of, like, this is like I'm saying similar the detail stuff is not. I enjoy the debugging and fixing, like figuring out how it works and making small fixes and but sitting there and writing this from scratch is people are really good at that. And,
the deepest I've ever gotten is really just into the like allocation stuff, but we don't need to go there.
Another time.
So keep going.
So for the most part, emitnative doesn't know about the target architecture. Now you'll see I'm making a liar of myself here because directly above this is a bunch of special cases for extensor. And the reason is that extensor is really weird.
Did you know so one of the weird things about extensor is the register windows?
Yes, exactly.
And did you know Dan was one of the people that came up with that?
Oh, really? Awesome.
Yeah, like when I was complaining about it when we first added S2 support, he was like, sorry, that's kind of my fault, and like linked me to a paper where he's like one of 3 authors that like came up with the register window stuff back with like RISC-V. It's just like incredible the things that Dan's been involved with.
It's like so many things that we see, right? That these really, really clever solutions to problems are really awesome if that's the only problem you have to solve. But when you also have to support x86 and ARM and whatever, it's so you can see extensor win is one of our it's basically 8266 and ESP32.
Oh, interesting.
Okay, so but for the most part, the emit native only has a high level API to the individual emitters, and so this is saying emit call with immediate argument, for example.
Mm-hmm.
So let's try and trim this down a bit. So like, does it happen if I remove the other clauses? Mm-hmm. So I'll run it again. Syntax.
You've got the rogue plus on 8.
Oh yeah, cool. Oh, that's the parser that does that. And okay, so without native, it's as expected, and with native, it's still wrong, which is good.
Okay.
Let's just do a quick sanity check and make sure like the world is not completely broken.
Do we have to call bytes?
Do we have to do anything, right? Like, sorry, we need a return, and that returns 0.
Which is correct.
So that's good. So yep, exactly as you said. The next thing is, do we need the bytes? And the answer is no. That first one. And does it matter what value this is? If I change this to 1 or 0, that's not important. But what if I get rid of that? I mean, as expected, now it should be back where we started. Yeah. Okay, so what's this line doing?
What if you do it as the first argument, first item in the tuple, not the second?
Good question. I'll make that 0 again. Good.
So it's correct.
Very good question. Yeah. So, what if we go back to what doesn't work, and we make it a local variable? and then do it. All good. So you'd think, like, if you looked at an optimizing compiler, you'd say that those two are the same thing, but this is not an optimizing compiler. This is going to be emitting, and we could look at that if I run VVV again. This function is oh, sorry, it's native. So if I turn off the native emitter, is storing it into local variable 1. So 0 is packed and 1 is A, and no, this is not.
It stores it and then loads it again. Yeah. It
Yeah,
stores
yeah,
it on
yeah,
13
exactly.
and loads it on 15.
Yeah. Okay, so that tells us something. So we've got sort of two candidates here. One is something is going wrong when we make it a tuple. So maybe we'll make it a list instead. Bad. Okay. Yeah, so something about it being the second argument and going into another structure, but only when it's in line in that definition, not in that invocation, not
Right. Not indirectly through a variable.
So at this point, we've got a couple of options. Like, I'd kind of like to rule out the fact that it's like the tuple or the list constructor going wrong, or at least let's confirm that by the time it gets to list, that it's the right thing to do. We've got a couple of options, but for me, like, I always just reach with GDB. And I could look this up. I could the steps to do this, but so I'm going to break on MP tuple MP. Oh, sorry, got to build with build with symbols. And break on MP tuple MP option tuple.
And
I'm
you
gonna
want
run
to see what it's given.
Exactly. I might just make that a bit bigger while we do this. So I've broken on option tuple, which I guess I should on the screen. Doing it this way. So MP option tuple takes the number of elements and the items. And so I receive 2 items as expected. The items are a list, so let's print items, pointer to where that list is. The first item is a number, and the second item is a number. Now, this is a good time to cover a pretty important concept, which is these might be surprising, that I'm calling new tuple. Remember, the output that I expected was 1, 0, but I'm seeing 3 and well, both not 0 and not 0xff. I've got this other thing. So what's going on here is these arguments are objects, MP obj t. And probably, if you walk away from one thing from this talk, an understanding of what an MP obj t is probably the most useful thing. So it kind of broke my brain initially when I first started learning about micropython that this is true, but it is actually true. Everything in Python can be represented in a variable. Like anything I could stash into a local variable or into a dictionary or whatever is an MP obj t. And the crazy detail is that MP obj t is just an integer. It's whatever. It's a little bit complicated because there's different representations, but all the different representations, they are just numbers. And it's depending on the architecture, it's either a 32-bit number or a 64-bit number. And the full explanation of how this works is in the top of mpconfig.h. And the reason for that is that there are 4 different choices for how MP obj t's work, and they did make sense for different trade-offs and different architectures. And the default is objwrapper A. I think on stm32 mpconfig.h, repo I think uses a default, which is A.
I think in
So-
CircuitPython we're exclusively C, but I could be wrong.
Okay. Yep. And the reason for C is you get floats. It's a huge performance. It's a huge optimization for floats. But
Right.
let's start with a simple one. So anything that can be stored in a variable internally in MicroPython is represented as a 32-bit unsigned number. And depending on the pattern of bits in that number, we figure out what the types are. So it's basically type tagging. So if the last bit is a 1, then this is a small integer. A small integer is a number that's small enough that we don't have to allocate it separately on the heap. And this is really great because it means you don't have to access the heap to do calculations on integers that are small. And so a small int is everything that you can fit when you take away 1 bit. So 32 bits left over.
This is why
so 31 bits.
This is why precision is 31 bits, not.
Exactly.
Yeah.
Yeah.
This is why people were like, when we're talking floats or ints, and Dan and I are like, it's not 32 bits. It's like 29 bits or 30 bits or whatever. That's because of this.
So this just the user doesn't care about this, right? So I can get 2 to the 31 minus 1. I can add 10 to that. Python doesn't care, but behind the scenes, what happened is that that object is no longer stored in the mp-obj. It's now an object that's on the heap, and we'll come to that.
Right.
And it takes care of this automatically. You can build MicroPython without support for this, in which case you are limited to just signed integers.
Right. We do have some builds in CircuitPython that do not have long int support, for example. So like trinket M0 for folks who run into that, like this is why.
The next representation is if the last bit is a 0, and then the next 2 bits are 0, 1, this number represents a Q-string. And so this is the intern strings that we talked about before. And so the value of this thing is a pointer to the string table. This is a huge efficiency for optimization for strings, which is that because remember, strings are two things. It's both literal strings, but also that your code is using. But it's also the name of like every global variable, every function, every identifier that's not a local variable name. So global variable names and function names and stuff. And so whenever I call the function unpack, I have to load unpack from the global stick. And the way I do that is, as we saw before, is I put that Q-string onto the into the opcode.
Mm-hmm.
And then the next is an object, in which case the actual, other than those last 3 bits, the value is the pointer in memory. So you can think of an object pointer as being just left shifted 3 bits and then ORed with that sequence. This is a thing for inheritance. Let's not get into that. I'm not sure. I'm not sure I do that justice. But
so David had a question that says, is there anything else than MicroPython that emits MicroPython bytecode? Like at one point, everyone was making JVM bytecode, even not being Java.
Yeah. Oh, interesting. Okay. So the simple answer is the cross compiler, but that is technically just MicroPython. So you can run on your PC, the cross compiler takes a .py file, generates a .mpy file to run on MicroPython. The way that works is it is just the Unix port of MicroPython or the Windows port, the special option enabled that can write out the mpy file from the in-memory representation. I've not seen anything else that does this though. Python's bytecode and MicroPython's bytecode is a bit different to JVM in that it is much more geared towards Python. I could imagine that would be possible. That would be quite interesting. Like it's cool to think like, what if you wanted micro PHP, micro Perl, micro Ruby? Could you write a Ruby Perl PHP to Python bytecode compiler?
I don't know.
Yeah, what I have seen is Blockly code, but it goes through the intermediate step of generating Python, so that doesn't really count, I guess. So. Good question. Okay, so the takeaway here is that everywhere in the runtime and the VM and the emitters, everything that you can represent in Python is a 32-bit integer.
Right.
And depending on the bit pattern, the way you interpret that 32-bit integer changes.
Right.
And when it's not a small int, not a keystroke, it's a pointer to an object on the stack, on the heap, I should say. And
it's not even. It could be in Flash, right?
Or in ROM. Yeah, good point. Yes, yeah.
It's just a pointer.
I never get it right which way it's Harvard or von Neumann, but because MicroPython is assuming the one where they're all the same address space,
right.
that works for Flash and ROM. Yeah. So when we're looking at debugger here, the reason that our value of what we're expecting to be 1 is actually a 3 is because it has it's been shifted to the left 1 and a 1 added on the end. Right. And so that's why we get 3. And similarly, 0xff shifted to the left 1 and added and 1 odd on the end is 1fff because that's just nine ones
instead of 8. Yeah.
And so that tells us that the problem is not in the generation of the tuple. The tuple is being generated with wrong information.
Right.
Because the number was already incorrect. Yeah.
Right, because that should be a 0. Or it should be a 1. It should be a 1, right?
This should be 0.
No, it should be 1 because it needs the 1 for the small n.
Yes, you're right. Yes, you're right. Yeah, sorry. Yeah. And of course, and I've changed this as well. So yeah, exactly. More work required. And obviously the problem here is the actually, and what we're worth looking at here is if I do a backtrace in GDB, it's a disaster because despite the fact I have symbols, it's come from code that was done by the native emitter, and that doesn't follow the stack frame layout that GDB expects, so it has no idea how to backtrace. But I could go up 1, and might work. No, it doesn't know. GDB just doesn't know what to do. What I could do is I could actually just dump the memory at this location and force it into the thing, but there's a better way. So, in emit glue.
So has anybody doing handwritten bytecode to do something smart or super optimized? I think generally the answer is no, because if you wanted optimization, you would not do bytecode level, right?
Yeah. I have to think about that. It's a good question. The bytecode quite closely matches the Python you write. So like if there were a more optimized bytecode, you could probably just write much more ugly, but otherwise the same. Otherwise Python.
One long line where you have no local variables.
Yeah, something like that. But on the other hand, though, for the native emitter, if you wanted to write more optimized native code, I don't know if CircuitPython uses this, but we have this dynamic native modules. So you can make MPy files from GCC output code. So you can write a function in C and have that be as if the native emitter generated it and whack it into an MPy file. If you want really highly optimized native code running dynamically on the device, then that yes. So and yes, we use that in a bunch of places.
And I think we did get that with the merges, and I think that Jeff revived the tests after I deleted them. So I think it does work. I think it does work, although I don't use it at all, and I honestly don't recommend it. But if you want to go there, you can go there. It's just you're not going to get help from me or anybody else.
Yeah. And there's a experimental thing that we're doing as well that hasn't gone very far, but we'd like to pursue is writing parts of the core in Python. So in the same way that Python call into native code, what we're looking at is having the actual native code of MicroPython, like the VM and the runtime, call into functions that are written themselves in bytecode. This goes back to the thing I said earlier, is that the bytecode is more efficient in terms of space. And a lot of functions that are written in the core, just because they need to be accessed by the core, don't really need to be written in C. And so, like, I think the pull request that Damien made, built in sum, for example. So, sum of 1, 2, 3. Sum is currently written in C in the firmware, but there's no reason that couldn't have been written in Python and been much more efficient. So
memory efficient, not execution efficient.
Exactly. Yeah, flash efficient. Yeah.
Flash
efficient. And so what we're looking at is some way to like literally write inline Python code in the C code sort of thing. Be pretty cool.
In the C code.
Yeah, we'll see.
You could do a similar trick to the way that we have Python stubs in our C code, just like make it a comment, but with like some prefix that designates it as Python or something.
Yeah, we'll see. But yeah, there's some pretty good efficiencies to be gained there. So I didn't know this off the top of my head, but what I did was I did know about micropython debug verbose. So that's quite a useful flag if you're trying to figure out the internals of the VM and the runtime and stuff like that. So when you turn this on, it turns on a bunch of things, but the most useful thing is it turns on this write code feature. So this is emitglue.c. It's kind of in between. My son is awake and he knows where the turn off all the lights in the house button is.
I was gonna say we should keep going here. I think your family is starting to wake up.
No, so that wasn't like a passive aggressive. I might get BBC Dad at some point, but we'll see.
I don't think we're that popular. Sorry.
So yeah, you can turn on micropython debug voice, but the one I care about is write code. And hello, Taylor's come to do some thumb assembly with us.
Awesome.
So you can tell that we've been here before trying to debug generated assembly because there's this little bit of extra code at the end of, and this is why being able to do this on the Unix port is useful as well, because it's literally using POSIX open, which wouldn't work on hardware. So I'm just going to do the lazy thing and I'm just going to force it to run.
Right.
And
I do that sometimes too. It's like, why would I set the flag when I could just comment it out?
I have to figure out that there was if statements up there and it'd be complicated. Now I can run micropython. I'm going to pull it again, and
you got an extra if. The last 3 lines you want to uncomment.
Those 3. Yeah,
uncomment those. Right, because the write code one is just through 166.
You're right. Yes, thank you very much. And so this I could turn on as well, but this is actually what this is what we got when I ran earlier. I know. I mean, I could basically what this would print is print the machine code in bytes. I have no interest in looking at, whereas this will print the same bytes but out to a file, which means I can use tools.
Right.
And now when I run my program with the failure, I will now have ID-TX1 outcode.
T.
Work.
You press T. You press
T for Taylor.
Mm-hmm.
Did that actually run? Emitglue compiled.
T. R for Taylor.
What am I missing? Am I running it from the wrong directory?
I for Taylor.
It looks right to
L
me.
for Taylor. L
You
for
could put a
Taylor.
print in there to make sure that you're running it.
I'm running the right micropython. I'm running that script. LS. I'll do that.
Where's P for Taylor?
Did I turn on the name emitter? Yes.
So David asks, is there a bytecode to Python decompiler? I don't.
That's a really good question. I keep saying that, but they're actually not really good questions. I have seen one. There's somebody named Kevin on, I think he's on your Discord as well, who's been looking into this.
Kevin Walters.
I'm not sure I've got the name. And the it would be quite useful. I've not seen one that's fully featured. Generally in a situation where you need to know what the disassembly would have been for like the people working on MicroPython, you're also generating the code, so you can just turn on the verbose output.
Right, you have the source, yeah.
Let's build that.
And press B for Benny. B for
Benny. Oh, sorry, I see what's going on. This whole this it's my fault for being lazy. This whole section is
it's in the
gated on. Is gated on this. So I'm going to
This is a whole nother level of programming, huh?
Benny, he's right. He's pressing T and B for Taylor, and Benny's his best friend. So.
Awesome. Well, he's learning to type real young there.
There
we go.
Ooh, there you go.
Taylor, do you want to get some breakfast? Yeah. Otherwise, it's been nice to see you. Can you say goodbye to everyone? Well, thank you, Taylor.
Bye.
Sure.
I know he can't hear me.
Okay, so now we have our code. Somewhere in my history of jumps, because I'm not going to remember that off the top of my head. So now I can use jump, which is great because I don't have to look at the. So it's printed out the whole thing, which is lots of zeros. But the that was my native code that was generated.
Okay.
Okay. Now, someone more skilled at this than I am could probably look at this and figure out the bug. But I couldn't. But I can.
That is not me either.
I have spent enough time looking at this that I can tell you roughly what the structure is.
You squinted?
And because we know kind of what to expect. We know what this function does.
Right.
And there's a test instruction, right? So this has got to be the branch, the if statement. So test followed by G. I don't see anything else that isn't moves and calls this function. So that's got to be the if statement. And we recognize a few things as well. So for example, the 1xff is exactly what we'd expect to see when we get the 255 case. So this is the
right.
So if we sort of thought about what's going on, we're jumping to 7e. 7e is down here, so we're jumping over the code that sets 255 in the object type representation. And otherwise we do and we jump over that to 88, which is there. So 88, I should say. Otherwise we do 1, which is 0.
Yeah.
So I wish I had done this when I first looked at this, but if I had spent the time to really think and understand what this code is doing, you'd see that this is the assembly code for generating this conditional statement.
Right. And this is x86-64, right?
Exactly. Yeah. And we could generate the ARM code for this as well, and I know x86 assembly better than ARM, so I would much rather work in x86. But
that's the opposite for me. I've definitely been exposed to Thumb more than ARM or than
Okay.
x86.
I'd be a bit lost. Okay, and so these calls are the calls back into the runtime. So what's happening here is you're loading into the AX register, the 64-bit A register, an offset of 0x80 from RBP, and then calling whatever we get as a result of that. And so showing in the code why this is the case is going to be tricky, but what's happening here is RBP in when you're running in native code points to the function table. So basically, the problem here is that there's no linker. We can't just say like call mp binary op. We have to like do all that ourselves.
Right.
So on entry to native code, we set RBP to be the function table, and then 0x80 is the offset of a function in the function table.
Mm-hmm.
And so I could actually look up in the function table what 0x90, 0x80, 0x168 are, and I native.
So one thing I thought would be interesting for folks, we were talking about code size, and if you look in this column, the left-hand side is the address, and then the next column that like varies in width is actually the bytes that are the instruction. So if you were looking at thumb, you would only basically have a single column there, because thumb is essentially, or you would have two numbers, because each number is a byte, and all thumb instructions are 2 bytes. All thumb 2 instructions are 2 bytes. Whereas this is varying because x86-64 is a variable length instruction encoding. And then the thing the next column is like the human readable version of that.
Okay. Yeah, exactly. Oh, yeah, good point. So this is the offset, like you said, offset. What the bytes would be,
right? And
then the disassembled version. So see, something I do a lot when I'm working in MicroPython is I should rely better on my editor to do QA Sublime, but it doesn't always figure out the cross references and stuff because there's a lot of preprocessor stuff going on.
I mean, for example, you use it way more than I do. I'll tell you that much.
So for example, if I wanted to find this MPF build tuple, it's not because it's a bit confused, but this is the function table. So these are the offsets.
Right.
And so what we would expect to find is that 0x80, which would be 0x80.
This is where I just have a Python terminal open.
Yeah. I think there's an implicit offset as well, but what we'll find is that one of these, I'm pretty sure, will be 90. So 90 is binary up, and then those 0x10. So 16 bytes earlier in that table. So 2 8-byte words is obvious true. Cheating it because I've been here before, but yeah, we expect our code to have emitted a binary op, convert it to being truth or not, and then do this comparison. So what our emitter is doing is saying, load a bunch of stuff, all mp binary op, do a bit more setting up, all mp obj is true, turn that into a 0 or 1, because like this could, we didn't know that the binary op returns a 0 or 1, right, or true or false. This could have just been an expression that returned an object. I mean, now we need to know whether or not it's truthy. Mm-hmm. And so mp obj is true. We'll turn that into a 0 or 1. And so then RAX is both the argument, is the function we're calling. The convention is that we also return in RAX. So what happens here is that when we call mp binary op, we've loaded the arguments, we call it, and we stash the result of that function into RDI, which will be RDI will be what we use as the first argument for the next function. And we then load the next, when we call mp obj is true, call it, and the result of whether it's true or not will now be in EAX. And then what we're expecting to do is then see if EAX is 0. So this is a common convention in x86 because it's the minimum possible representation, is that we just look at the low byte. And because we knew that all the other bytes were 0, look at the low byte only and see if it's 0 and jump if 0. So what's going on here? Randomly in the middle of this, between calling obj is true and checking the result, we write 1 to EAX. Then do some adjustment, and then write. We write 1 to EAX, and then we write the 64-bit EAX, the extended EAX, into an offset on the stack. And I wish I could tell you that this is how I figured out the first time. I did a lot more printfs and a lot more GDBing. And that was because I wasn't comfortable enough looking at this disassembly and figuring out exactly what was happening. But what I eventually found is I turned on print statements. So for everything that the native emitter did, so that would be one thing that native emitter did. That would be another. That would be a call to object true. Right. That would be a call to MP binary op. And if we look at emit native, emit native binary op, emit native binary op, in that case that we looked at before, actually says emit pre-pop reg, emit call, if it was an invert, emit another call, and emit post push reg. So when we go and look at emit binary op here, this is the setup of the arguments, the push pop, etc. This is the emit call. And so this whole section here is this whole section there is what you get as a result of the compiler telling the native emitter to emit binary op. I mentioned Viper just for completeness. The other case here is when the types are all integers, and Viper knows that their types are integers, and so instead of emitting a call to binary op, it literally emits a left shift or emits another left shift. There'll be all the different ands and ors and all that sort of stuff. And so that's why Viper is so fast, because instead of emitting all of that to call a function, which is a whole lot more work, it literally just will emit.
It just does it.
Add or whatever, and then knows that it's unsigned or signed. Okay, so
I do want to.
Where does this come from?
Folks are commenting in the chat about how deep of a deep dive this is, and let me reassure folks that like this is probably the deepest that I've ever. It's certainly the deepest I've ever gone on CircuitPython, but I've been in industry since I graduated in 2009. Like I've never gone this deep for even stuff I did at Google beforehand. So like it's hang out. This is the deep dive. Enjoy it. Don't think that you need to follow it. Just like all the other stuff I do. Like you can figure it out given enough time. Just like Jim did.
Like I said, I'm condensing, a day of work, right. And I have done this before as well. So like but the cool thing is about micropython, literally approximately 0 people need to understand how this works.
Approximately 2 people, Jim and Damien.
If you are watching this live stream and you're like, this is exciting and interesting, come and talk to us about the RISC-V emitter, and or figuring out a way to optimize this, right? Like if you're familiar with stuff, you're probably screaming at this disassembly here and being like, what the this is terrible, and so optimizing this would be really cool and have some huge performance benefits for MicroPython.
Right.
I might skip through what's happening here because getting to the bottom of this is a bit complicated. But
I mean, what we know, that's the trick, right?
Yeah, what we know. So we now know what's at fault. We've mistakenly, and so in assembly program we'd call this clobbering, and so we're using the EAX register for a particular purpose. And between using it for something and using it for something else, we've used it for another thing.
Right, you're overriding it.
And so what we know is that we're in the middle of the ternary operator, which I'm going to cheat ever so slightly because I know that we're in emit native jump helper. So the way I would have figured this out is either with the debugger or with print statements to find out that immediately after the binary op and before the immediately after the is true and before the jump.
Right. So what you've done is you have this something if something else value, right? Like value if condition else other value. And so what we've done is the first thing to do is figure out like what the condition is, right? So what you're saying is like, okay, we've completed getting the thing inside the condition part of that thing. and now we've kind of like gone one level higher, and now we're going to figure out based on that how to produce a value.
That's exactly right. Yeah. And so with a bit of work and so debugging in printfs, I will find that the thing that is emitting the is true happened. I mean, we know it's got to emit and is true. So what we could do is
we made Jim get up early this morning.
we're in the weeds, so let's not do that. But what I would do is I put a debugger on the code that emits the is true, and then I would see what the very next thing it does. And the very next thing it did was call emit native jump helper, which is to be expected because we're emitting a jump, because it's all if statements are jumps. So once again, we can ignore the cases where the types aren't pyobj because we're not using Viper, so therefore all types have to be pyobj.
Okay.
And so we emit pop of the register, which means that we need to take the current value off the stack. This is the value that we're going to be making the decision on. This is a fancy way to say whether or not I want to push it back on the stack. So this just like moves the stack back again, which is that we don't have a peak register.
Right.
Doesn't matter. We get the top value off the stack.
And then you might adjust the stack back so it's again back on the stack.
Exactly. Yeah. And then we call obj is true, which is what we expected.
Right. So this is taking whatever object was returned and deciding whether it's true or not.
So at this point we are here. We've called mp binary op. Now figuring out if it's true or not.
And so what is the next thing we do?
Almost like, this is kind of amazing when this happens, but like the code actually tells us exactly what's going wrong here, because here's the bit where we do the jump.
Right.
We do this thing, and right in between it, we do something else, right? So we've set up the register with the result of mp obj is true. We're going to make a decision on that. We did other work in the meantime.
Right.
So here's where I have to explain 3 different stacks. So the processor has a stack, sort of natively. There's a bunch of instructions to work, like push and pop and stuff like that. And that's the same stack as the C stack. So when you call a function in C, that's the same stack that operates on. In MicroPython, the function itself has a stack, which is not on the C stack, although that is a compile option that you can enable. And so what I haven't gone into detail on, but this.
So where does that live?
Yeah, the C stack.
Okay.
But what happens is that the emitter actually goes through multiple parses, and on an earlier parse, it's figured out how many local variables there are.
Oh, sorry.
And that crazy detail I said earlier is that all objects are just these mpobjts, which are all just 32-bit numbers. We just figure out how many local variables there could possibly be in every possible branch of the code. That's how big the stack needs to be. And we make room for that on the C stack. But it is not managed by the C stack, right? It's not using the stack pointer register and stuff like that. We have our own stack pointer. And if that is too big to put on the stack, we put it on the heap instead. So there's a little code path that does that. Then the emitter itself has a stack that is managing its use of that stack that's operating. And so now this is where there are a few cool optimizations, which is that if we can avoid emitting code for manipulation of variables, we don't. So a good example of this is like, if I add an immediate to the stack, I could just ignore putting that on the stack if I immediately then pop it off afterwards and stuff like that. So the details here are really complicated and messy, but the point of this function here is, and this comment explains it pretty well, is that we have these 3 different stacks, and we're about to do a jump, and we need to synchronize them to make sure that they're all consistent. Because if we jump, things will be messy.
Right.
And so need stack settled basically says, do I have stuff in the emitter stack that is not currently code genned in the Python stack? And it turns out we do. And this is where this particular case is really interesting. So what this expression does is it's making a tuple out of these two values. So if we simplify it to return 0, 0, it pushes two immediates onto the stack and calls np option new tuple, the pointer to the stack, but offset by 2. And so it pops two values off the stack and then makes a tuple out of them.
Right.
And
so
what we've done here,
the third stack, so it's the processor C stack, it's the micropython stack, and then it's the emitter stack.
yeah, but the emitter stack only exists while we're doing the emitting. It's not a runtime stack, but it is also managed as a stack, and it can be modified by the emitter, and the emitter can then realize that it didn't actually need to do operations to modify the Python stack, the runtime stack. Right. And so it's a really neat optimization that does save a lot of generated code.
Mm-hmm.
And so what's happened here is that when we do this, we will get to the end of putting these things on the stack without actually generating any code. And then we'll realize that we're going to emit a call to new tuple, and we're like, oh, okay, we've got to actually get them onto the stack so that emit new tuple can access them. And what's happening here is that we emit an immediate that temporarily doesn't do anything. We then do this if statement, but now it's like, we've got to settle the stack.
Right.
Make sure that this value really does get onto the stack. Because this is a really simple example, but these two branches themselves have sub-branches and stuff like that and do all other things with the stack. And so depending on which branch we take, we need to do different things.
Right.
And so need stack settled literally just says, go through the emitter stack. If we have any registers, and the other optimization that's really cool is that we can avoid using the the Python stack and not entirely put things in registers instead. So for some local variables, they will in fact never touch the stack. They will entirely be kept in registers.
Right.
So the emitter can realize that this value never even needs to become on the stack at all. And so that's the other half to this. And
the benefit for, like, to tie it back to what we talked about earlier, is that the closer you have your memory to the CPU, the faster it can run. So, like,
exactly.
Registers are the fastest memory you can use because those are, like, in the CPU themselves. Whereas the stack is going to live, the stack is going to live in RAM, but for complicated CPUs, there may be, like, layers of caching between the actual RAM and the CPU as well.
Yeah, and orders of magnitude difference.
Right.
There's a really awesome, it's probably about a thumb, the rules of thumb, numbers programmers should know thing, and it gives you like the orders of magnitude of what these things are. And not only is it faster, but it's fewer instructions to access, right? Because if I want to access the value in a register, it's just a mov or an add or whatever, but accessing the stack involves moving things around.
Okay.
And so it's worth zooming in on Sublime to look on what's happening here is that what we do is if we have stuff in registers, we now need to put into the Python stack. We just emit mobs, so it goes from the register, a mob from the register onto the stack. So that's not going to clobber anything because you can do that, just register the stack. If I have an immediate in the emitter stack,
right?
So that's
so this is 0. A number you were holding on to that you didn't know exactly when you needed it. So we're gonna wait to do something with it until we know when we're gonna need it.
Exactly. And what I'm going to do is load it into a register, because it's at the moment it's just ephemeral, right? It's in the emitter stack. I'm going to load it into a register on the CPU, and then I'm going to copy that register into the Python stack. Right. And do you want to take? I'll give you one guess. What do you think reg temp 0 is?
It's the return register.
CAX, yep. Exactly. So, and we can check that. So for the x64 RAX. And so, as you can imagine, keeping all this state in your head and figuring out all possible paths and how these functions all interact is so hard, right? So that's why this is a subtle bug that's probably existed for many years, right? And
right.
And when you look into this in detail, and I'll save the analysis because that's actually there's quite a lot of paths you have to follow. This is the only path that calls need stat settled with an outstanding state. So fortunately,
Right. So
we actually
that's
tick
kind
lots
of
boxes.
what is the name for that? Like your invariant. Like
Yeah,
you
that's
should
good.
only call need stack settled if none of the registers are available.
Exactly. And so I had a chat to Damien about this issue, and one of the outcomes, the conclusion was note clauses. Yeah, and when you do like lots of like proper assembly, like there's lots of cool ways that you can add metadata to say this thing clobbers this thing, and in general, MicroPython, this whole pre-pop, there's you probably would have seen a bunch of things about emit pre and emit post is all about actually, and in here, caller save versus callee save is about the guarantees that these are the invariants that we provide. Like these variables are all, you can't rely on them being saved at any point, whereas these ones you should. And
Right.
we are breaking that. We are breaking that invariant.
Right, and that's known as calling convention. So, right. So
Yeah.
when you
It's
look at
part of
like
the convention.
if you look at like RISC-V, like they have an ISA, but then on top of that they have like calling conventions or something on top of that that's like if you compiled C code, here's like how we're gonna like use these registers in a standard way for
And that
exactly
ties
this
in,
reason.
this ties into the ABI for the architecture for the
ABI.
platform. Yeah.
That's the
Application binary.
binary interface. Yeah.
Exactly. Yeah. Which specifies your calling convention. Yeah.
Right.
And so there's a couple of options here. Well, we should write a test, but so here's another case where this is used, but in this case it doesn't matter because there's no like temporary state that we need to worry about that then is used later. There is temporary state, but it's not used. The result doesn't matter here.
Right.
But in this case we do. So we've got a couple of options. One is that we could settle the stack earlier. We could spend a bunch of time analyzing all these paths and figure out like, and I think I convinced myself that you could call need stat settled here because we know that obj is true probably won't mess things up. But much simpler alternative is that we know we're going to club our RAX, but we're not going to club our RDI and RSI, and they give us the same guarantees. So the solution is, like all good bugs, it is a 2-character fix.
You just change which register it goes into.
Yeah.
Okay.
And so now, if I save that, okay, so let's run it. I get 0, 0.
Yeah.
As expected. And if I look at the after I run it, if I look at the disassembled output,
Those two instructions will still be there, but you'd be using a different register then.
exactly. So it's those two are still there, but now I'm moving into EDI instead of RDI. And then I guess I should check.
It's probably your debug.
Yeah, tell them all about it.
I always leave my debug prints in too.
Taylor's little T for Taylor.
T for Taylor.
That way. And we'll come back to that. So to tie things up, obviously what I should now do is write a test. And and the way this works, for people who haven't seen it, is I would write. So the way our tests work is we have these Python files, and we expect them to run the same on MicroPython and CPython on different platforms.
Right.
And if we can't run the code on CPython, then we provide what the expected output is. But I would write a file here called like native settle stack or something like that, and come up with a few test cases and add it with this PR. Cool. So that's flashed to the PyBoard, and I should be able to run 0, 0 on my PyBoard as well.
Nice.
So the same fix fixed it for thumb,
Right.
um,
Right.
which is a relief. And if I check that reg temp 1 on asm thumb
Ah.
is using, it is a different register. All platforms provide 3 temp registers, and it is a different register, so to be expected there as well.
Right. Different from the return register.
Confusing, yeah. Temp 0 is often the same as the return register, but temp 1 and temp 2 will be different. So
Right.
yeah, that's a good way.
Right.
That's a good way to think of
Awesome.
it.
So what should we do to wrap up? First, I think if folks want to follow along with this, what is the issue number?
Yeah,
under MicroPython.
It's e7523.py. So
Oh.
I think I even have it open.
7523.
Did I say 7523?
I think so. Yeah.
Cool. So Twisteroid Ambassador, we're very grateful to for raising this in the first place, and a really, really awesome case. Like really grateful that wasn't 100 lines of code that we had to.
100%.
And then I should have done this in the live stream, but this is to show a bit more detail about what's going on with the stack. I put a few more variables, and then you can really see that they are the small int values. Sorry, this is probably hard to see.
I see what you're saying. There's more stuff that gets settled.
Yeah, exactly. And so you'd actually see a lot of settling happening, clobbering AX as it goes. But it's otherwise the same. And then at the point that I wrote this, I didn't know what the solution was.
Right.
I spoke to Damien for some to confirm that was in fact the right thing to do. And so after this, I just haven't got around to making a PR for it yet, but I will.
It is Saturday for you, so you shouldn't work.
Oh yeah, I'm not doing it today. But I will.
Matt points out that this is an example of why it makes no sense to pay devs by the lines of code they write.
Yeah.
The time is in figuring it out, not fixing
It's not
it.
the most exciting single. Well, there's a 2-character change, but I do have a story from a long time ago where not me, but a coworker added an ampersand to a file, and so it was C++, so it changed something from being a pass by value to pass by reference, and it was a piece of very, very hot code path. And it was just a typo. Somebody had missed the pass by reference, and it was, hundreds and hundreds of thousands of dollars a year worth of GPU time saved as a result. So there's lots of these. They're pretty good.
Yeah, I remember there was a time when I was at Google, and there was a loss of Gmail accounts that they eventually restored, but it was all caused by a missing asterisk, I think.
I remember that one. Yep.
Yeah. Great. Well, Jim, thank you for taking us to the deep depths of MicroPython. And as I've said earlier in the stream, really, this is why we build off MicroPython, why we try to support MicroPython as much as we can, and why I think everybody watching should be doing that as well. Go ahead. So I guess one way to do that is by sponsoring them on GitHub. Is a good way to do it. You can also buy hardware. I think it's probably still in stock. This is also the type of work that I've always offered to pay Damien to do for CircuitPython. I don't think, Jim, do you have a company?
I work for Damien. So
right. So Damien has George Robotics, is Damien's company, and that's who pays Jim. And I assume that the MicroPython sponsorship money goes through there as well. But yeah, this is the sort of benefits you get from paying devs to work on stuff.
And we are extraordinarily grateful for all of Adafruit and CircuitPython support for the GitHub sponsorship as well from Adafruit is fantastic, and
Yeah.
it's really cool. And like I said before, I'm really excited to be working more closely together. And just this week we had a great example of that where feature was implemented in CircuitPython that we're now adding stream. So
Yeah, the split types.
yeah, and that's really cool, right? Saves a couple of kilobytes on our really constrained ports, and no, it's really good.
Yeah, I think, we had that meeting between the five of us, like you, Damien, and Jeff, and Dan, and I, and it felt a lot like a software team, like, who never meets, right? Because, like, we all work in the same place, we work on the same code, and we think about a lot of the same similar things. So it's cool to have those communication lines open, even if we're not in the identical same code base all the time. Yeah, so this has been great fun, Jim. Thank you for taking me into more of the emitter stuff. I think if people want to try this on CircuitPython, the code should be there. It's just like not necessarily enabled or tested on our part, but we don't actively like turn it off. I don't think so. So if people do want to get into these weeds, but still be in CircuitPython, you're able to do that. This is all within that core like Py directory that we share with MicroPython, and that we've talked about sharing kind of like more structuredly in the future. But yeah, so this is
And
go ahead.
thank you very much for all the really good questions.
Yeah.
Lots of really good details that we got out of those questions. So thank you very much.
100%. Yeah. So thank you to everybody who hung in to the technical difficulties at the start, including Jim, especially because all of the Australian folks got up early. It started at 7 a.m. in Australia. So thank you to Jim for being the guest, and thank you to all the folks in the chat who are in Australia or other time zones as well, who carve it out of their day to come hang out with us. This has been a deep dive with Scott on Adafruit here. It happens normally 2 p.m. Pacific time on Fridays. If you want to support me, and you can do that by going to adafruit.com and buying some hardware there. No hardware launches during the stream today, but it wouldn't be out of the question. That does happen from time to time. You can also purchase Pi boards from Adafruit if you're in the US and like that's convenient. We do. Obviously, that supports the MicroPython folks as well. If you want to hang out, Jim's on the Adafruit Discord as well. You just have to ping him. Although, don't DM, never DM people. But you can ping people in public places. You can join the Discord by going to the URL adafru.it/discord. I'm on there as well. You can feel free to ping me. Don't DM me, but you can ping me if you have questions. The reason to do it in public places is that other people may be able to answer your questions as well. So with that, I think that's it. Jim, thanks again, and you're always welcome on the deep dive.
Yeah, it was really fun. Thank you, Scott.
It's been a blast, and I learned a lot myself. I haven't looked at x86 assembly before, so that was new for me. Yeah, when do we get CircuitPython on the Pi board? So you can load CircuitPython on the Pi board already.
Yep.
Once we started supporting the STM stuff, we added support for it. So yeah, with that, I don't even know if CatCam's running, so we'll just say thanks again to Jim, and we'll see you all next week. Check out MicroPython if you haven't.
Thanks, Scott.
Thanks, Jim.